All right, so in this video, we're going to sketch the function y is equal to the inverse tangent of x minus 1 over x plus 1. Step 1, the domain. What is the domain of arctangent of x? The domain of arctangent of x is all real numbers. So we can input any number we want into arctangent. So we're going to look at x minus 1 over x plus 1 now, but it's not like, if let's say this was log of x minus 1 over x plus 1, well, then we would have to analyze x minus 1 over x plus 1 from the sense that, well, we can't have 0 or a negative number come out of that. We don't have any restriction in this case with x minus 1 over x plus 1, except for, whatever could potentially be restricted by that itself. In other words, okay, you have a polynomial divided by a polynomial, no restrictions there, but you can't divide by 0 though. Okay, so the only restriction here is going to be x can't be equal to -1, right? As long as x is not equal to -1, you can input anything you want into this function and you're going to get an output. Okay, so the domain then is -∞ to 1, and then 1 to infinity. There's everything except for the value, or -1, sorry. Everything except for the value -1. Okay, the range. Well, when you think about the range of arctangent, it's limited to like between plus or minus pi/2, something like that. So we're going to have a limited range, but we'll analyze that later in the video. All right, intercepts. What are the y-intercepts? Let's set x equal to 0 and solve for y. So -1 over 1. Arctangent of -1 is equal to what? Okay, so arctangent -1 is minus pi/4. Okay, so we're going to go, let's plot this intercept here, this y-intercept. So we're going to go from -5 to 5, and then on the y-axis the same, 5 to -5. All right, now what is pi over 4? -0.79. So 0 minus 0.79. So 0.51. So right around in here. Okay, that's the y-intercept. What about any x-intercept? So we set y equal to 0 and solve for x. Okay, so did we input the equation yet? No, okay. Arctangent of x minus 1 over x plus 1. Store that as e. Very good. Okay. Now we want to solve e is equal to 0 for x. X is equal to 1. Okay, so that's an x-intercept. X is equal to 1 is here. All right. Now let's look for symmetry. Is this an even function? So y of minus x is equal to, so minus x minus 1 over minus x plus 1. And let's just put this in here. So minus x minus 1 over minus x plus 1, you get the original function back. Or do you? X plus 1 over x minus 1? No, you don't. It's the, yeah, you do not. You do not. So this is not equal to y of x. Okay. Now minus y of x is equal to now perhaps does this simplify to something? I don't think so. No. Okay, so this is not equal to y of minus x, so we don't, it's not an even or an odd function. Now, what about periodicity? Is there some number p such that y of x plus p is equal to y of x? We've got an inverse trig function, but inverse trig functions are not periodic like the trig functions are, so no. No. All right. There's no symmetry. Next, the endpoint behavior. So let's go to the endpoints of the domain and take the limit as x approaches the endpoints. All right, so the limit as x approaches negative infinity of the function is equal to pi over 4. Okay, the limit as x approaches positive infinity of the function is equal to pi over 4. So we've got a horizontal asymptote at pi over 4. Okay, what is pi over 4? 0.79. Okay, so here's 0.5, here's 1. And there's pi over 4, positive pi over 4. We're going to be approaching this as x goes to in positive and negative infinity in some way. Okay, now another endpoint is the minus 1 here. So what we want to do is we'll consider that an endpoint as well. When we look at the domain, we're looking at, going to the left and the right ends of the domain, but any endpoints in the domain as well. So minus 1 is another endpoint. So let's go ahead. We'll call that endpoint behavior. Let's take the limit just to see, because we might have, maybe this is a vertical asymptote. Okay. Let's take the limit as x approaches minus 1 from the left of the function. Okay, limit of the function with respect to x approaching minus 1 from the left. Pi over 2. Okay, what is the limit as x approaches minus 1 from the right? I believe this is continuous, so this should be pi over 2 as well, but we'll check. Minus pi over 2. Okay, interesting. So it's not continuous. Okay, so this is really we need to do this to solve this graph, to sketch this curve. You see, the function, you might say, well, oh, so it's two different values for the same input. Minus 1 is not part of the domain. Minus 1 is not an input. We're just seeing what the function approaches as x approaches minus 1 from both sides. It's not approaching positive or negative infinity in any one of these cases, so there's no vertical asymptote. It's approaching, when it coming from the left, it's approaching pi over 2. So what that's telling us is that, so pi over 2 would be somewhere, up here, let's say, and minus pi over 2 down here. Okay, what that's telling us is that the function coming to minus 1's here is going to be coming up like that, or coming from the top, whatever. We'll see. and approaching here. And then and from this direction, it's going to be doing like this to some degree, approaching minus pi over 2. But it's not going to, we're going to have open circles here. It's not going to be defined here. Oh, well, no, I messed that up. It'll be coming to here. It'll be open circles here. Okay? All right, critical points. Okay, let's start with the first derivative. Okay. dx. Okay. So there are no critical points here because there's nowhere where this equals 0 and there's nowhere where this doesn't exist. You can't plug anything in here to make it to divide by 0, so none. All right. What about the second derivative? Okay, at x is equal to 0. And then there's nowhere where this doesn't exist, so that's it. Okay, when x is equal to 0, it's 0 minus pi over 4, okay? So 0 minus pi over 4. So here the second derivative is going to be equal to 0. All right. Now we need to do the intervals of increasing, decreasing intervals, and the intervals of concavity. All right. So for the first derivative, we'll have, so 0 and then minus 1. We could switch here. So x is equal to minus 2. So increasing in this region. And then x is equal to 0 for the first derivative. It's increasing in this region. Okay, so there is no change. It's increasing everywhere. What about the second derivative? So we'll check at minus 1 and we'll also check at 0 for the second derivative. So, okay, the second derivative with x is equal to minus 2. Okay, concave up. What about x is equal to minus 0.5? Concave up. What about x is equal to 1? Concave down. Okay, so this is going to be an inflection point. The curve is continuous here. We know that at x is equal to 0, and we switch, the second derivative switches signs. There's no local maxes or mins. Well, actually, no, there might be, because this is, we just saw that this is kind of like, at x equal to minus 1, it's kind of like a discontinuity. It is a discontinuity. It's a jump discontinuity. And so you can have a local max or min at a discontinuity, but you won't be able to tell if it is or not based on the first derivative test. Okay, so let's graph this. We need to graph pi over 2 and minus pi over 2. So pi over 2, 1.57. So minus 1 and then 1.57. So 1.5. So about right here. We'll put an open circle there. Minus 1, 1, minus 1.5. So about right there. Open circle. There we go. Okay. Now, we know the behavior of the function as it approaches minus 1 from the right and from the left. It's just going to be like a regular curve just approaching this value. So we come through this point, we're just going to be doing like that. Or like that. We're just going to be just coming up to this value. It's like the function is just continuous, just approaching that value. That's it. Okay? So let's go to the left of -1 first. As x approaches negative infinity, the function approaches pi over 4. All right? So it'll be, you know, coming in this direction, but it'll be what? The -1 concave up increasing. And there's no critical points here to where we have like a local min or something. So this will be pretty simple. Just like that. Concave up, approaching this horizontal asymptote, increasing. And then just as x approaches -1 from the left, just approaching that pi over 4, or pi over 2, plus pi over 2. Okay? Now, coming from here, we're going to be concave up as we approach 0. So we'll be doing like that. And then we'll switch to concave down, so something like that. We'll be increasing this entire time. So what else do we have? As x approaches positive infinity, we approach pi over 4. So okay, so we're going to switch to concave down, right? We should be switching to, we should be concave up, then switching to concave down. Is that right? That's right. Okay, so we don't do what I just did was wrong. That's like a local min. No, it's just approaching it. There you go, like that. You see how it's concave up here? You see that concave up, and then it switches to concave down. But it's always increasing. It's increasing everywhere. So that's the inflection point. That inflection point is also the single y-intercept, and we also have the x-intercept here. So there you go. That's the function. Now, okay, well, let's actually come back in this video. Let's come back to the range. What's the range? The range is going to be minus pi over 2 to pi over 2, not including the endpoints. Okay, that's it. That's the sketch of this function.